I'm Nathaniel, and this is a brief review of catalytic fast pyrolysis. So what is catalytic fast pyrolysis? Well, it is the thermochemical conversion of biomass into bio-oil, and it is a renewable energy. Typically, researchers will take the leftovers of industrial agriculture or lumber milling and turn that into bio-oil. Right here's a picture of bio-oil. It's dark brown or black, and it looks pretty much similar to oil refined from petroleum. So how does it work? I'm not going to get into the ins and outs of this machine. This is a pyrolyzer, and I don't know how they work. The important thing is the biomass is fed through this feeder, and it is burned in the absence of oxygen, um, which vaporizes the biomass. Those vapors are then collected and treated with catalysts in a process known as catalytic cracking and upgrading, and that's where we get our bio-oil from. So why is catalytic fast pyrolysis important then? Well, aside from global warming concerns that we all know about, our global consumption of fossil fuels is increasing while our supply is decreasing. In fact, about 99.43 million barrels of liquid fuel were consumed per day in 2022, and this consumption is expected to increase. So we need to find alternatives, ideally, that are compatible with current hydrocarbon fuel infrastructure and don't cause nearly as much greenhouse gas emissions. And that's why bio-oil has the attention of so many researchers. So why isn't bio-oil being used right now then? Well, there are several constraints with bio-oil conversion. The first of that is deoxygenation of bio-oil, and the second of that is the catalytic regeneration and coke accumulation. So here are some functional groups, oxygen-containing functional groups that we find in bio-oil. Like I said, the deoxygenation of bio-oil is a huge issue. And why is that? Well, the oxygen-containing functional groups that I have here on the left contribute to high acidity, high viscosity, high moisture, low heating value, corrosiveness, and chemical instability of the bio-oil. Um, a highly viscous fluid will clog fuel lines in machinery, so obviously that won't work. And a lower heating value just means that you're not getting as much energy from the bio oil that you do from, let's say, gasoline, fossil fuel derived gasoline. So, with that being said, how are researchers trying to get around this? Well, researchers use a plethora of catalysts. I am going to be talking about zeolite catalysts today. And zeolites are a microporous material made of mainly silica and alumina, and they are used in the refining and production of chemicals and crude oil. The main role of these catalysts is the deoxygenation of bio-oil, and for the most part, they actually do a pretty darn good job of it. Here's an example of what this process looks like. It by no means is this rigorous or robust. Um, on the left here, I have just like a generic hydrocarbon chain that you might get from pyrolyzing your biomass, and you want your catalyst to crack it and deoxygenate it. So ideally, this is your product. Um, a shorter hydrocarbon chain with no oxygens, resembling more like the gasoline that we have and that we put in our cars right now. Of course, it's not quite that easy. These catalysts create quite a bit of side products. Yes, they do create some oil and they are quite good at deep deoxygenation. However, they create really big side products like these polycyclic aromatic compounds. These compounds will get really, really big and then they accumulate onto the catalyst as coke, which is just carbon. And what this does is it blocks the active site of the catalyst, meaning it can no longer crack more of these biomolecules obtained from our biomass. This is an issue because the bigger and bigger these polycyclic aromatic compounds get, the more difficult they are to remove from the surface of the catalyst. If you imagine these compounds getting much, much bigger and getting onto the catalyst, while the vapor pressure decreases and the boiling point increases, meaning that these will not burn off at reactor temperatures, and these reactors get quite hot between 500 and 700 degrees Celsius. So obviously that's a huge issue for researchers. If you're creating side products that ruin your catalyst and you can't get them off, that cannot work in the long run. So what are researchers doing about that? Here's a brief side on Coke. So this is a fresh catalyst, and this is a coked catalyst. And again, Coke just blocks the active side of the catalyst and makes it useless. So here's what researchers are doing. They are modifying their zeolite catalysts to select for smaller side products like benzene, toluene, and xylene. The positives of this are that they don't get really, really big polycyclic aromatic compounds. They still get coking of the catalysts. However, they are a lot easier to burn off and regenerate. So that's a big plus. You get your deoxygenated bio-oil right here, and then you get smaller side products which don't ruin your catalysts. What we want, though, excuse me, another issue with this is that zeolite catalysts that are really good at deep deoxygenation and select for good side products, they don't take very much of the carbon from the biomass and turn it into bio-oil, which economically is not very good. We want as much biomass as possible to end up in oil as opposed to these lighter side products. On the inverse, catalysts that are really good at getting carbon from our biomolecules aren't very good at deep deoxygenation. So we have this push and pull between, okay, well, do we want really deoxygenated bio-oil but not very much of it, or do we want a lot of bio-oil that's of not very high quality? And that's currently the state of catalytic fast pyrolysis. So, to conclude, for the economics of catalytic fast pyrolysis to make sense, as much carbon as possible from the biomass needs to end up in oil. Generally, there is a correlation between the carbon yield of oil and oil oxygen content. High oxygen content allows for high carbon recovery, while deep deoxygenation results in low carbon yields. Catalysts that can escape this correlation are of great interest to current researchers. Thank you.